Let's see oscillations. We are interested in basically simple harmonic motion in this chapter. But to understand simple harmonic motion, we will understand oscillations. Now, you already know what do we mean by oscillations. If you oscillate this thing, when I say oscillate this thing, that means what? This to and fro motion. This is something we are interested in. Now, most of you would say that it's a simple pendulum. It is not. This marker is called a compound pendulum. What is a simple pendulum? What is a compound pendulum? What is oscillation? What is simple harmonic motion? What is periodic motion? These are the things we will study in this chapter, and we'll also find time periods for different bodies. For example, when you oscillate this marker, what is the time period? We will try to find these things in this chapter. Now, the first thing which you need to know is periodic motion. Second thing is oscillatory motion. And the third thing, which we are basically interested in, is simple harmonic motion. Now, do one thing. First, write down periodic motion. When an object moves such that it repeats its motion, after a certain time interval, then that type of motion is called periodic motion. And this time interval is called its time period. For example, circular motion with constant speed. Now, if something is moving in a circle with constant speed, then you know that it is going to repeat itself again and again after a certain time. And therefore we say that circular motion is an example of what? Periodic motion. What is the other example? The simple pendulum, which you know. What is a simple pendulum? When you only have a point mass, that is called a simple pendulum. If you connect a point mass with a rope, then that is called a simple pendulum. Whereas if you have a rod like this, then this is called a compound pendulum. If you hold your book, if you hold this duster, and this is called compound pendulum. But if you look at this duster, then you can see that it is repeating its motion again and again. So we say that a simple pendulum or a compound pendulum, their motions are also what? Periodic. Write down this. The examples, first example is what? Circular motion with constant speed. The second example is motion of a simple pendulum. And motion of a compound pendulum and motion of a compound pendulum. Now, this is periodic motion. You repeat yourself again and again after a certain time interval. Now, look at the difference between circular motion. If something is moving in a circular path, then it's like this. Whereas if you look at a simple pendulum, this is the ball. This ball, you know that it moves in this direction, then comes back, goes to the negative side, and then comes back. It oscillates like this. Did you see I said oscillates? Now, you don't see any oscillatory motion in this. You can see a to and fro motion in this setup. They both are what? Periodic. This thing is going to repeat itself again after certain time. It's back to the same position. Again and again, it is going to repeat itself. Right here, this ball is going to repeat itself again and again after a certain time. And therefore, they both are what? Periodic motions. But there is a difference between this and this. And for that difference, we introduce what? The second type. Write down the second type, which is oscillatory motion. Oscillatory motion is also a periodic motion. Oscillatory motion is also a periodic motion. But in this, an object moves to and fro about a given point. But in this, an object moves to and fro about a given point. For example, motion of a simple pendulum. For example, motion of a simple pendulum or motion of a compound pendulum or motion of a compound pendulum. That is circular motion. That is circular motion and simple harmonic motion. Circular motion and motion of a pendulum. Circular motion and motion of a pendulum. They both are periodic. But circular motion is not an example of oscillatory motion. But circular motion is not an example of oscillatory motion because there is no to and fro motion. There is no to and fro motion about a given point. There is no to and fro motion about a given point. If somebody is at this point, you always find that object is moving this way. Whenever it reaches this position, it's always moving in this direction. And therefore, it's simply what? Periodic motion. Whereas in this, if you look at this position, if it starts moving this side, it's moving this way, comes back, now it's moving that side, comes back, now it's moving this side. And therefore, about this point, you see to and fro motion. It is repeating itself and therefore is periodic. You have to and fro motion and therefore it's called what? Oscillatory motion. Now, let's talk about this third part. You'll understand this third part later when I introduce basics of simple harmonic motion. But a rough estimate we can always develop. Write down the third part, simple harmonic motion. Simple harmonic motion is a periodic oscillatory motion. Simple harmonic motion is a periodic oscillatory motion in which restoring force in which restoring force is directly proportional to displacement of the object from its mean position. Displacement of the object from its mean position. What is mean position? What is restoring force? What is displacement from the mean position? And what do I mean by proportionality? We'll see it later. As of now, simply remember what is simple harmonic motion. It's a periodic motion. It is also an oscillatory motion in which restoring force is proportional to your displacement from the mean position. For example, motion of a simple pendulum or of a compound pendulum with small amplitudes. Amplitude means how far you go with respect to this position. This position is called mean position. We'll see later. This side, this much, these things are called what? Amplitudes. What happens if you have a pendulum and if you give it a very large displacement and you release it? This is called angular displacement. If you give it very large angular displacement, then it is periodic, it is oscillatory, but it's not simple harmonic. Why not? We'll see later. But if you give this pendulum small displacements, then it describes simple harmonic motion. Just don't worry about simple harmonic motion as of now. Right now, our aim is to understand difference between periodic and oscillatory, and we will automatically understand what simple harmonic motion is. Now, note down this much first, and then we'll start with simple harmonic motion. Note down this. Now let's see how oscillatory motion takes place, and then we will define simple harmonic motion. Consider this situation. You have a point which you call origin. That means x is 0 at this point. X is 0. If you are on the right hand side, you know that x will be positive. If you are on the left hand side, x will be negative. This point, x0, is origin. Now, suppose you have an object which is at this position, and force which is acting on the object, somebody gave us this force, 4 times x. A force is acting on the object, and that force is given as 4 multiplied by displacement of the object from origin. This origin we call mean position. We'll see later. Don't worry. F is what? 4x. Now, my question is, if f is 4x, then is it possible to have an oscillatory motion? Think about it. If a force of 4x is acting on the object, then is it possible for the object to describe an oscillatory motion. Then look here, f is 4x, which means what? If you are on this side, which is the right side, x coordinate is positive. If x coordinate is positive, then on this side, force will be positive. If force is positive, what is the meaning of positive sign? Positive means east. That means on this object, you have a force which is acting on this side. That means what? This object under this force is going to move towards the positive x, that is east, and it will continue moving this side. It will never come back. And if it doesn't come back, you do not see any to and fro motion. If there is no to and fro motion, that means you do not see any oscillatory motion. Suppose this object is on the left side. Let's again see this part. If object is to the left of origin, on the left side x is what? Negative. If x is negative and you use this force, then force will be negative. Let's say at this position x is -2. If x is -2, then this says force is what? 4 into -2, which is -8. What is the meaning of negative sign? Negative sign means left or west. That means force on the object is pointing towards left. This object under this force will move towards negative infinity. It will never come back, and therefore again you do not see any to and fro motion, and we say that it is not an example of oscillatory motion. Cross means no oscillatory motion. No oscillatory motion. Now, let's take another example. In this next example, same point, x is 0, this side x is positive, this side x is negative. We have an object and force on the object is minus of 4x. Somebody gave us that force acting on the object is minus of 4x. Now, if our object is on the right side, if it's on the right side, x coordinate is what? Positive. X is positive, but what is force? Negative. For example, if x is +2, then this says force is -8. What is minus sign? If you say that force is coming negative when x is positive, that means force is acting in this direction, this way. And when the object is on the left hand side, you see that x is what? Negative. Say -2. If you put x -2, then -4 into -2, it becomes what? 8. That means force on the left side is coming what? Positive. What is positive? Right side. This direction. That means if object is on the left hand side, then force is acting towards right. That means this force tries to move the object this side. And once it crosses origin and reaches over to this side, then you see that force changes its direction. It acts in this direction and moves the object back to this position. Where force, you can see, is acting in this direction. It comes back, goes like this. You can see we have started to and fro motion, and therefore we see an oscillatory motion. In this case, oscillatory motion is possible. Now, let's take a third situation. Now we'll do all these things fast. This is x equals to 0. This side x is positive. This side x is negative. If somebody says that force is 4x square, 4x square, I hope you can see that oscillatory motion is not possible if object is at this position. Force is what? Positive. That's the direction of force. If object is over here, force is again what? Positive. X is negative, square of that is positive, force is coming what? Positive. Which means what? This object is always moving, whatever be the position, under this force to the east side. And therefore it will continue moving towards positive infinity. It will never execute to and fro motion, and therefore we do not see any oscillatory motion. Cross means there is no oscillatory motion. Now, if I ask you for the same setup, that force is minus of 4x square. Force is what? Minus of 4x square. Then pause the video, think about it for this thing, whether it will execute oscillatory motion or not. Then come back and see the solution. Now, if force is minus of 4x square, then what happens? If object is on this side, this is origin, this side, over here your x coordinate is positive, x is positive, force is coming what? Negative. Force is in this direction. Force is in this direction, but once you cross the origin and reach to this side, over here, your x coordinate is what? Negative. If x coordinate is negative, square of negative, positive. With this negative sign, your force is coming negative. Your force was coming negative. That means it is still acting in this direction. Which means this object, when released, will move towards negative infinity. It will never come back. There is no to and fro, and therefore it is also not an oscillatory motion. So by now you must have seen that if you have a positive sign or if you have a negative sign, which always remains there, negative, negative, there is no oscillatory motion. Force is positive. Force is positive. If force remains of same type, about both sides of the origin, then you do not see any oscillatory motion. Whereas in this case, you saw that force is negative, force is positive. This is the oscillatory motion, and therefore we can introduce something like this. First, this x0, somebody gave us force as 4x cube. We know that it cannot be an oscillatory motion. If x is positive, force is positive. If x is negative, force is what? Negative. X is positive, force is negative. It changes sign, but in what way it changes the sign? Look at that. This is x0. If you are over here, your x coordinate is positive. Right here, your x coordinate is negative. Then what? On this side, x is positive, force is in this direction. Arrow represents direction of force. Object is going this way. If x is what? Negative. If x is negative, q of negative is what? Negative. Force is coming negative. Force is acting this way. That means in this case you saw that force, its direction is different. It is negative and it is positive. Then we see an oscillatory motion. In here, that is happening. Direction of force is different. We see an oscillatory motion. The answer is no, we do not see. Then what is the difference between this force and this force? That is called restoring force. This force tries to move the object towards the origin. It tries to restore it at the origin. If you move it to the left, it tries to move it back to the origin. Whereas in this case, you see different signs. But once you displace an object from the mean position, it does not come back. In fact, it moves towards infinity. If you move it to the left, it doesn't come back and moves towards minus infinity. And therefore, this type of setup will never give you an oscillatory motion. For an oscillatory motion, on both sides of the origin, you must have different directions of force. And those different directions should be such that they behave as restoring forces. Which means if somebody gives us this type of thing, that f is minus of 4x cubed. Now look at this, minus of 4x cubed. Think about it, whether it is an oscillatory motion or not. Give it some time, pause the video, think about it, whether do we see an oscillatory motion or not, and then come back and see. So, this is origin, x equals to 0. An object, this side x is what? Positive. If x is positive, force is what? Negative. You see a different direction of force. Force is negative. If you are on this side, x coordinate is negative. X is negative, cube is negative. Minus 2, its q is what? Minus 8. That minus with this minus becomes what? Plus. Force is in this direction. Force is what? Positive. You see what? Change in the force. And the ultimate thing is what? This force, it is always directed towards a particular point. This point is called mean position. Whenever you have a restoring force type of system, in these restoring forces, they try to move the object towards the mean position, which is defined as x equals to 0, which means a position where no force acts. We'll see this statement later, but as of now you can see that if you can produce restoring forces, then that will define an oscillatory motion. So, no oscillatory motion. Oscillatory motion is present. Oscillatory motion is present. There is no oscillatory motion. Negative sign is in front of it, but there is no oscillatory motion. Direction of force, it's not changing. In this case, although force is positive, force is negative. You see different signs, but These signs, they do not represent restoring sense, and therefore it is also not an oscillatory motion. But once you arrive at this setup, you see that you change the direction of force, and every time this force is acting towards the mean position, and therefore you get what? An oscillatory motion. Now, write down the statement. For an oscillatory motion, for an oscillatory motion, we must have a restoring force or torque. For linear, we say force. For angular, we say torque. We'll see that. For an oscillatory motion, we must have a restoring force or torque type of system acting on the object. Now, by now, you know that if we have a force in this form, negative sign, some constant, it's not about 4, it can be 5, 6, anything, x to the power n. If you have a positive sign, you know that it can never be an oscillatory motion. If this is positive, then there will be never an oscillatory motion. You must have a negative sign, so that this negative sign changes x and f. Position is positive. Position is to the east. Position is to the east of mean position, but force is acting due left. That will happen with the help of negative sign. Now n. What should be n? You can see that this n should be an odd number. If you have a force of this type, then that will give you a very basic oscillatory motion profile. F equals to minus some constant x to the power n, where n should be what? Odd. Then this is the guarantee of an oscillatory motion. You can remove this 4 with some constant. Write down k. Remember, this constant k should be positive. Why? If k itself is negative, then negative and negative, they will become what? Positive. If you have a force of this profile minus some constant x to the power n, where n belongs to the odd category, then you will always have what? Oscillatory motion. Now, if I ask you what is the simplest odd number, then you know that simplest odd number is what? 1. Simplest odd number is what? 1, which means f is what? Minus of k x to the power n, which is what? 1. This is the simplest odd number. This is an example of oscillatory motion, but this oscillatory motion has a special name which is called simple harmonic motion. This is the thing which we are basically interested in this chapter. If you have a force of this type minus of some constant x directly proportional to x, then this is a periodic motion, also an oscillatory motion, especially simple harmonic motion. So in all these things, you saw that this is what an oscillatory motion. This is also an oscillatory motion. But look at this oscillatory motion, minus of 4x. So this minus of 4x will be called simple harmonic motion also. Whereas this thing, minus 4x cube, this minus 4x cube, is it oscillatory motion? Answer is yes. Is it simple harmonic? Answer is no. Why? Because power of x is not 1. So, whenever you have a force, what is the meaning of negative sign? Negative sign, it does what? It changes direction. If you're on the positive side, force is this way. If you're on the negative side, force is this way. What is it called? Restoring force. So this negative sign means this is what? Restoring force. If your restoring force is proportional to x, what is x? Displacement from origin, which is called what? Mean position. If your force, which is called restoring force, is directly proportional to x, then that type of oscillatory motion is called simple harmonic motion. Put down this, and then we'll see how to handle this f equals to minus of kx. Around this much. Now let's investigate this f equals to minus kx. First of all, f equals to minus kx. F is proportional to what? Minus x. Negative sign means this force is restoring force. Write down a point. In f equals to minus kx, negative sign means restoring force. Restoring force. X is always taken from the mean position. X is always taken from the mean position, and mean position is that position, where net force on the object is 0. Where net force or torque, if you talk about angular SHM, is 0. You can say it, if x is 0, force is 0. That means you are at the origin. That origin, which we discussed, was basically what? Mean position. What is mean position? That position where you see no force or torque. Look here, in this case you can see the torque. If I hold the marker directly down like this, then it does not experience any torque. You know that mg, force of mg, that is passing from the axis. This is the axis, and therefore you do not see any torque. The moment I displace it this side, mg, which is acting at the center of mass of the rod, this mg, it produces a torque about this axis, and it comes like this. If I move marker this side, it will move towards the mean position. What is the mean position? That position where you see no force or torque. So F is proportional to minus x. X is not displacement. Remember, it can be considered displacement, but somebody says that if somebody says that object is released from 4 meter, look, if it's released from 4 meter from this side, let's say we are discussing linear motion. So this is 4, this is the starting point. From the starting point, if after some time it moves to this side, and right here your x becomes 3. What is x? Distance or displacement or position from the origin. So what? Look here, what I'm saying. This is x equals to 0. Somebody releases an object from this position. At this place, x is what? 4. And then it moves to this position. At this position, your x is 3. This is what? Mean position. It started from this and then arrives at this position. From x equals to 4 to x equals to 3. What is displacement? 1. In this particular setup. 1. So x is not displacement. What is x? We say that x is displacement of the object from the mean position. Write down this. X is displacement. X is displacement from the mean position. Now, or you can simply say position. What is x? Position with respect to origin. Write down like this. Or we can say that x is position with respect to origin. Somebody here, if I ask you what is x, you will say 4. What is x? 3. Position with respect to origin. Now, if this is force, then what is acceleration? Acceleration, you know, is what? Force divided by mass of the object. That gives us minus of kx divided by m. This minus of k by mx is spatially written as minus of omega square x. This omega square, which you see, is nothing but k upon m. K upon m. Minus x minus x. What is omega square? K upon m. This omega is root over k by m. This omega is called angular frequency. Angular frequency. Why is it called angular frequency? We'll understand that. Why do we write it as omega square? Why didn't we write it as omega or something else? Why was it square of angular frequency? You will understand it later. As of now, you just remember that there is some constant, and that constant is omega square. Why is it omega square? We'll see that. But if it's omega square, which is k by m, then omega is root over k by m, which is called angular frequency. What is angular frequency? What is natural frequency? What is time period? You will see all those things. This angular frequency, its unit is radians per second, just as the unit of angular velocity. What is angular velocity? Radian per second. This is what angular frequency. This is also equivalent to angular velocity. We'll reach there later. This omega, which you see as root over k by m, is also 2 pi upon t. Why? Later. What is t? Time period. This t is called time period. As of now, simply write down these things. You will understand everything. This omega, which is root over k by m, is also what 2 pi upon t. This you have seen in circular motion. Circular motion. At the same time, this omega is also called 2 pi f. This f is called natural frequency. Natural frequency. Unit of natural frequency is 1 upon second, or something more familiar, which is hertz. Omega is root k by m. It's called angular frequency. Is equivalent to angular velocity, but we'll see that later. Radian per second. From that angular velocity part, you will understand this. From that angular velocity part, you will also understand this. This f is called natural frequency. Natural frequency means if I say 7 oscillations in 1 second, then this f is 7. If you say 100 oscillations per second, then this f is what? 100 hertz. That's what you mean by f and all. Now, once you define a as minus of omega square x, now this a equals to minus omega square x is fundamental equation of linear SHM. Linear, angular, later, linear. So this a equals to minus omega square x is the fundamental equation. Of linear simple harmonic motion. Linear SHM. Note down this much. Now, once we have acceleration as a function of x, then it's basically kinematics. Motion in 1D. Linear, straight, that is motion in 1D, and we can find velocity, displacement as a function of time, and all these things. That's what our aim is. First thing is, we need to find velocity of an object undergoing simple harmonic motion as a function of x. Write down the heading. Velocity of an object undergoing SHM as a function of x. As a function of x. And for this, we will define A. A is called amplitude. What is amplitude? Amplitude is called maximum displacement from the mean position. Maximum displacement from the mean position. Write down, capital A is called amplitude, which is maximum displacement from the mean position. At amplitude, you know something. Let's talk about this and just look at the tip. If you look at the tip, and if angles are small, just assume that this tip is executing what? Linear simple harmonic motion. So the tip part, as it moves, this position, the farthest position from mean position, that's your amplitude. On this side, let's say this is 4, then you will say that amplitude is 4, or x is 4, When you're over here, your x becomes minus 4. If I say that amplitude is 4, that means an object can move plus 4 and minus 4. Between these two boundaries, it will remain. So, this is x equals to 0, which is origin, which for us is mean position. That's your mean position. This is the maximum displacement, maximum you go from the mean position. This is x equals to plus a, or is called positive amplitude. This is also a, but is given by minus of a. X0 plus a minus a. Now, there is something about velocity which you know at amplitudes. If this body oscillates, you can see the moment it reaches amplitude, its velocity becomes what? Zero. Instantaneous velocity becomes zero. It reaches this, it comes at rest. So at amplitudes, you know that velocity of the object is what? Zero. At amplitude, you say that velocity of the object is what? Zero. Now, with this, we can develop this using fundamental equation of linear SHM. So we have a equals to minus omega square x. We need what? Velocity as a function of x. We use v square equals to u square plus 2as. Kinematics, we can use this equation. But there is a problem. We cannot. These are called Newton's equations. They are used for one-dimensional path, which it is. But at the same time, for these equations, acceleration must be constant, which it is not. Our acceleration depends on x. As x changes from 0 to 1 to 2 to 3 to 4, your acceleration is changing. And therefore, we cannot use Newton's equations. Write down this. In simple harmonic motion, we cannot use Newton's equations of motion. We cannot use Newton's equations of motion as acceleration is not a constant. As acceleration is not a constant. So if acceleration is not a constant, then what? From kinematics, we know that acceleration is also dv by dt. And this dv by dt is minus of omega square x. dv by dt. What is A called? Instantaneous acceleration. What is that? dv by dt. What is that? Minus omega square x. Now, many times people go for this. They write dv minus omega square x dt. They go and integrate this thing. Integration of dv is v. Omega square. Integration of x is what? X square by 2. Integration of dt is what? T. This is wrong. You cannot integrate it like this. Because this is not x dx. What is integration of x dx? X square by 2. But this is x dt. You cannot integrate it. There are three variables v, x, t. At this stage, you cannot. So, what should we do? Look here. This is dv by dt, which is minus of omega square x. Let's multiply on both sides with v. When you multiply on both sides with v, right here, you will write dx by dt. After all, what is v? From kinematics, dx by dt. What is a? d by dt. What is v? dx by dt. You have multiplied same thing. That means your original equation is what? Same. We cannot do this. Now, you can cancel dt and dt. Once dt and dt are gone, this is what? V dv equals to minus of omega square x dx. That's a very basic integration. I just told you x dx, its integration is what? X square by 2. And therefore, this thing gives you v dv, its integration will be v square by 2 minus of omega square x dx. What is the integration of x dx? Integration of x dx is what? X square by 2, and integration is not complete. You need to have what? Constant of integration c. That's your c. How do you decide c? How do you find c? Can you see? Can you see? It says that when x is a, v is what? 0. This equation says if you put x in this equation, you will get v. Now, you already have this information. When x is a, amplitude, v is what? 0. Let's put this in this equation. When you put it, it becomes what? v0 x a. And you found the value of c. We have found the value of c, which is coming omega square a square by 2. And this c is this. Put it back in this equation. When we put it back in this equation, it becomes v square by 2 minus of omega square x square by 2 plus c, which is omega square a square by 2. 2 cancelled. This is v square, take omega square out, a square minus x square, which you can write as v plus minus omega root over a square minus x square. This is the final result for this article. An important part you need to remember. What is v? Plus minus omega root over a square minus x square. Now, do you understand the meaning of plus and minus? What do I write plus and minus? Any oscillatory motion of this type, you say it's quite symmetrical about this position, mean position. Left side and right side. So it's basically what? The thing which is left for you is right for me. You're facing like this. And therefore, if somebody says that this is left, if you ask him to stand behind the board, then he will say that this side is what? Right. In an oscillatory motion, this side and this side, they both are what? Identical. The only change is of direction. Direction means what? If an object is at this position, then at this position and at same distance from the origin, from the mean position, same distance, you will have same behavior. The only change will be in what? Direction only. If somebody is standing at this position and at this position, you will find same type of v. That's the reason you see x square. Try to understand it. This is, you don't have to worry about it a lot, but if you can, it will be a good thing. Suppose I say that for this position x is 2. Then for this position x will be minus 2. Now, at x equals to 2 and at x equals to minus 2, where will you find greater velocity? You will say that both places are identical. To this side, to this side. Now, since they both are identical, you must get same magnitude of v. And that is possible if you get x square. If x is 2, 2 square is what? 4. If x is minus 2, minus 4. So you are getting same magnitude. That's the reason maths has given us this x square. You don't need to know this reason, but if you know it, it's a good thing. Now, look at the plus minus sign. At this position, how many types of velocities do you see? Once you're moving towards the amplitude, then you're moving towards the origin. So while moving towards the origin, look here. I hope you can understand this path. So, at this position, object is moving in this direction. At this position, object is moving in this direction. And if I say that this is x equals to 0, this is x equals to 2, then what is this? Then we will say this is x equals to minus 2. No, this is still what? Plus 2. You are on the right hand side. When you are this side, it will be called minus 2. This is not plus 2. This is still what? Minus 2. Now, you are at x equals to 2 twice. For this, object is moving this way, and you say that v is coming positive. For this, look at the direction. Object is moving this way. X is positive, but what is the direction of velocity? Left, and therefore v is negative. That means for a given value of x, if it is 2, let's say, you get two values of v, plus and minus. Same is the case with this. If you change x as minus 2, everything is same magnitude wise, but at this point, your object is moving in this direction, and at this point your object is moving in this direction. You can see again that you've got two values of velocities, plus and minus. So you now understand meaning of plus and minus, and also you understand why do we have x square. Last thing in this part, if I ask you what is the maximum velocity in simple harmonic motion, magnitude, write down the question. Find out maximum velocity in simple harmonic motion. Pause the video, note down everything, come back, and I'll try to answer this question. It's a very easy thing. I'm looking for maximum value of velocity. Now, again, pendulum. As it oscillates, you know that at amplitude, velocity becomes what? 0. Then, force is acting this way, restoring force. As it moves and reaches mean position, force is continuously acting in this direction. This object is continuously being pushed, and therefore it gains what? Velocity. Just when it crosses the mean position over to the side, direction of force changes. Now direction of force is this way. Object is going that way. Force is this way. That will decrease the velocity. At this amplitude, it again comes at rest. Then, if you are on the negative side, you know that restoring force, it will act this way. This force brings it back to the mean position, but by the time it comes back, it has gained some velocity. It goes to the positive side, But now force, it changes direction, velocity starts decreasing again, it reaches the amplitude, velocity becomes zero. So where is the place? What is the place where you see maximum velocity? That place is what? Mean position. Write down this. In simple harmonic motion, maximum velocity is at mean position. Maximum velocity is at mean position. And what is the magnitude of that? You've got the formula. Mean position is what? Origin is what? X equals to 0. What is velocity at x equals to 0? Use this. X0 gone. What is that? Omega root over a square, which is a, and therefore V maximum, it is found at mean position. And what is it? Magnitude wise a omega. Magnitude means you're moving sometimes towards east, west, east. That's the mean position. Now, every time you pass from the mean position, your velocity is maximum and is what? A omega. Note down everything. This is also an important result inside the boundary. Note down this.